Good day, everybody. Today, we'll be talking about gases. In this chapter, first we'll introduce to you the kinetic and molecular theory. Then we'll talk about different gas laws, such as Boyles Law, Charles's Law, Avogadro's Law, combined gas law, and ideal gas law, etc. Kinetic and molecular theory is a model for understanding the behavior of gases. This model predicts the correct behavior for most gases under many conditions. It works the best for the low pressure and the high temperature. The gases behave more ideally under these conditions. Like other models, the kinetic and molecular theory is not perfect and breaks down under certain conditions. For example, high pressure and low temperature, the KMT breaks down. We focus on the conditions where it works the best. As we just emphasized, gases will behave more ideally under lower pressure and higher temperature, and those gases are so-called ideal gases. In the kinetic and molecular theory, an ideal gas is a collection of particles in constant moving, and they always move in a straight line until the next collision, and the particles will neither attract or repel one another. And in other words, the particles will have negligible attractive forces in between. And between the species, it's mostly empty space, so the molecules behave like sizeless points. They are considered as sizeless dots. And the average kinetic energy of the ideal gas is directly proportional to the absolute scale temperature in Kelvin. The higher the temperature, the faster the gases move on average. I would like to emphasize it's the kinetic energy, not the velocity of the molecules, that is proportional to the absolute temperature. According to kinetic and molecular theory, gases are expected to have some properties as listed over here. For example, gases are compressible. Gases assume the shape and volume of their container, and gases have low densities in comparison with liquids and solids. Let's look at a few questions. All of the following are postulates of a kinetic and molecular theory of gases except number one, the volume occupied by a gas is mostly empty space. This is correct. According to kinetic molecular theory, gas molecules are considered as sizeless points. B. The average kinetic energy of the gas particles is proportional to temperature in Celsius. This one is misleading. The average kinetic energy of gas molecules is proportional to the temperature in the Kelvin scale. So B is wrong. So B is the answer that we pick. Let's continue for learning purpose. The attraction repulsion between gas molecules is very weak or negligible. That is one of the assumptions for ideal gases. So that one is the correct statement, but we pick the wrong answer to this question. D. Gas molecules of atoms move in straight line between collisions. That is correct. So B is the one we pick because that is the wrong answer. Before we continue, I would like to introduce to you how to describe the properties of a gas. For a gas sample, we have four variables to describe the state of a gas. First is pressure, second is volume, third is number of moles N, and the last is the temperature. So P, V, N, T, or pressure, volume, moles, and temperature combined can describe the state of a gas sample. What is pressure? The pressure is the result of a constant collisions between the atoms or molecules in the gas and the surface surrounding them. So the gas molecules collectively keep punching on the surface or the surface of the container. Since pressure is the result of collisions between gas molecules and the surfaces around them, the amount of pressure increases when the number of particles in a given volume increases. Because of pressure, we can drink from straws, inflate basketball, and move air in and out of our lungs. And the variations in the Earth's atmosphere creates wind, and changes in pressure helps predict the weather. Pressure is all around us and even inside us. So what is the pressure generated by a gas sample? The pressure exerted by a gas sample is defined as the force per unit area that results from the collisions of gas particles with the surrounding surfaces. Pressure is the force over the area. The most commonly used unit is atmosphere, or ATM. The SI unit for pressure is Pascal, or PA. It's defined as 1 Newton per square meter. It's the force over the unit area. You need to be familiar with the conversions between different units of pressure. For example, 1 ATM is exactly the same as 760 milliliter of mercury, because in the experiment, the 1 atmosphere pressure can actually push up 760 milliliter of mercury. Notice in this tube, the top end is actually vacuum. Remember, 1 millimeter mercury is also called a torr. It's after the Italian physicist Torricelli. 1 millimeter mercury is the same as 1 torr. And the height of mercury can be converted to 29.92 inch. 1 ATM is also the same as 14.7 psi, or pounds per square inch. Let's look at one example. Convert 0.311 ATM to millimeter of mercury. We know 1 ATM is 760 millimeter mercury, so these two units are directly related. For this reason, we can convert ATM to millimeter mercury using 1 ATM is 760 millimeter mercury, but we keep ATM at the bottom, so it cancels out with the original unit, and we convert this to millimeter mercury, and the final answer is 236 millimeter mercury. Now let's talk about the different gas laws. The first gas law is the Boyles gas law. It talks about the relationship between pressure and volume. This relationship was discovered by Robert Boyle. Boyle's law states the volume of a gas and its pressure are inversely proportional, assuming constant temperature and a constant number of gas molecules. Please note that when V and P are inversely proportional, we can also say V is directly proportional to the inverse of P, or P is directly proportional to inverse of V. This tells us, as you can see in this picture, when P increases from left to right, V decreases. When V increases from bottom to top, P actually decreases. A good example would be you have a balloon, you hold it in your hand, and you try to compress it and try to bounce back because P increases. But when you squeeze it, the volume will decrease. Please note, when we talk about P and V relationship, P and V is inversely proportional to each other. Mathematically, it's the same as saying P times V is a constant. Or, under different conditions, condition 1 and 2, P1 times V1 is the same as P2 times V2. And Charles's law can be used to explain some of the behaviors or some of the rules we should abide by in scuba diving. And scuba divers, they know really well about the Boyles Law because it explains why ascending too quickly toward the surface is dangerous. The pressure regulator used in scuba diving delivers air at a pressure that matches the external pressure at depth. Otherwise, the diver could not inhale the air. When the diver is 20 meters of depth, the regulator actually delivers air at the pressure of 3 atm to match the 3 atm of pressure around the diver. The reason is because the 1 atm is due to the normal atmospheric pressure, and the other 2 additional atmospheres is due to the weight of the water at 20 meters. Remember, every 10.33 meter of water will generate 1 extra atm. So it's about every 10 meters, it's equivalent of 1 atm. So when the diver is at 20 meters of depth, the water will generate 2 additional atmosphere. If the diver inhaled a lungful of 3 atm air and swam quickly to the surface, where the pressure will drop to the atmospheric pressure, 1 atm. If the diver is holding his breath, according to Boyles Law, if the pressure decreases by a factor of 3, then the volume of the air in his lungs would increase by a factor of 3. So this will severely damage the lungs and possibly killing the diver. So divers must ascend slowly and breathe continuously, so less air will be trapped inside. This will allow the regulator to bring the air pressure in their lungs back to 1 atm by the time they reach the surface. Let's look at a calculation based on Boyles Law. Remember, for Boyles Law, P and V is inversely proportional to each other, or P times V is a constant. But this is not practical in the calculation. More practical equation would be under condition 1, P1 times V1 will be P2 times V2. So in this question, a cylinder equipped with movable piston has an applied pressure of 4 atm and a volume of 6 liter. What is the volume of the cylinder if the applied pressure is decreased to 1 atm? Apparently over here, there are only 2 variables changing. Remember in the very beginning, we talked about there are 4 variables to describe the state P, V, N, and PVN, and the T. We use the 4 variables to describe the specific state of a gas sample. So if only P and the V are changing, then that tells us the number of moles N and the temperature T, they are not changing in this case. Only under these situations, Boyles Law will be valid, and the P1 times V1 will be P2 times V2. So we use Boyles Law, P1 times V1, P2 times V2, because we only have P and the V related in this question. P over here, V, and then we ask you if we change the pressure to 1 atm, and we ask the volume. So you have a P1, V1, and this is V2, and the P2. Okay. So you substitute the numbers into this equation, and you find out V2 is 24 liter. Let's look at another question. A gas has a volume of 1 liter at 1 atm. By what factor must the pressure change in order to reduce the volume by half? Remember, this is the typical application for Boyles Law. Boyles Law tells us for the pressure to reduce the volume by a half, then the pressure must increase by 2 times, or it should be doubled. B is the correct answer, because P times V is a constant. Charles's law discusses the volume relationship with temperature in Kelvin scale. And this relationship is discovered by Charles, a French mathematician and a physicist. Charles's law states the volume of the gas and its Kelvin scale temperature are directly proportional to each other. Or you can write it in V directly proportional to T. When one variable is directly proportional to another, you can write it as, for example, V is directly proportional to T. That means when V increase, T will also increase. When T increase, V will also increase. And the ratio of the two will be a constant. And this can also be written as V1 over T1 is V2 over T2. As you can see, when temperature increases from left to right, the volume increases as well, as you can see in this picture. You might have also noticed in this lower temperature range, we have no dots over there. That's because under low temperature, the gases will behave less ideally. In order to predict the situation, if the gas were behaving ideally under low temperature, then we have to extend the dots from the known trend. When we predict this trend by extending the line on the plot backward, so we can know how they would have behaved under low pressure. And this process is so-called extrapolation. Our extrapolated line shows that the gas should have a zero volume at negative 273. This is a negative 273 degrees C, or more exactly, negative 273.15 Celsius degree. And this corresponds to the 0K, the coldest possible temperature. And 0K is also called the absolute zero, because you cannot have temperatures below that. Let's look at the picture for one more time. Notice that, as we mentioned, there are only experimental data for relatively higher temperature, and we cannot experimentally determine how this gas sample behave at the lower temperature range. The reason is because under low temperature, the gas will behave less ideally, thus they will not follow the same trend. So to predict how the gas would have behaved if it's an ideal gas, we extrapolate this. So basically we extend this line for the lower temperature, and this will give us the lowest possible temperature, which is the absolute zero, or 0K, which corresponds to negative 273 degrees C. If temperature is changed when the balloon is moved from the ice water bath into a boiling water bath, the gas molecules inside it move faster due to the increased temperature. If the external pressure remains constant, as we see over here, the external pressure will be the same as the atmospheric pressure. In this case, the volume will change when the molecules expand the balloon and collectively occupy the larger volume. Please note that the external pressure remains constant in this case, and the balloon will not have a leakage of the gases. And in other words, N is the number of molecules inside is also the same. So for Charles's law, this is valid, but external pressure P is a constant, and the number of gas molecules trapped inside is also constant. So P and N, they are kept constant. Let's look at one application. A sample of gas has a volume of 2.8 liter at unknown temperature. So here we have a volume V1 at unknown temperature. So this is T1. When the sample is submerged in ice water at 0 degrees C. So we do have the temperature in Celsius scale. Do remember, in Charles's law, V1 over T1 equals V2 over V2. The temperature must be in Kelvin scale. So T2 is 0 degrees C, but you got to convert it to Kelvin degree, to Kelvin scale. And V2 is also given. That's 2.57. So we substituted the numbers in Charles's law. V1 over T1 is V2 over T2. So we can find out T1. And do remember, convert T2 to Kelvin scale. 0 plus 273 gives you the Kelvin temperature. That's 273. So substitute all the numbers in, V1, V2, and T2 in Kelvin scale. So first, you find out the unknown temperature to be 297 Kelvin. You got to convert it back to Celsius degree as well, because it does ask you to find out the temperature in both Kelvins and the Celsius. So for the Celsius temperature, it's the Kelvin minus 273. This gives us 24 degrees C. A flexible container contains 1.50 liter of gas at 25 degrees C. What is the new volume when the container is heated to 100 degrees C at a constant pressure? So do remember, here we have, this is V1, and here that's T1 in Celsius degree. And what is the new volume when the container is heated to a new temperature? So this would be T2. The reason I use the lowercase is because it's in Celsius degree. We have to convert it to Kelvin scale. This question is asking you what is the new volume, and this is V2. So we can do the calculation using Charles's law. V1 over T1 equals V2 over T2. Remember, the temperature T1 equals not 25 degrees C, but 25 plus 273. So this converts Celsius to Kelvin, 298 K. And T2 is 100 degrees C. We convert it to Kelvin scale as well. This gives us 373 Kelvin. So substitute the numbers to this Charles's law. V2 equals T2 over T1 times V1. So you substitute all the numbers in. V2 will be 373K divided by 298K times 1.50 liter. And this gives us a number of 1.88 liter. E is the correct answer. So far, we have learned that Boyles Law tells you how P and V are related at constant temperature, and Charles's law shows how V and T are related at constant pressure. Remember, in both cases, the number of moles of gases in the sample do not change either. So if we combine these two variable changes, so rather than having two variables changing, this time we're going to have three variables changing. How would this work? This will give you P times V over T is a constant. Or in other words, P1 times V1 over T1 is P2 times V2 over T2. And this law is so-called combined gas law. To remember, the temperature in any gas law, including this combined gas law, must be in Kelvin scale. Let's look at one example. A sample of gas has initial volume. So I would like to remind everybody, when you are reading this question, I want you to label this. So that's our V1, right? At the pressure, so this is our P1, and the temperature, so that's our T1. Now, if the gas is compressed to a volume of 108 milliliters, so that's our V2, and heated to a temperature of T2. Okay, and what is its final pressure in milliliter of mercury? So this would be our P2. Apparently, in these two conditions, we have three variables changing. So we need to use the combined gas law. Do remember, the T must be converted to Kelvin scale. Okay. So T1 is 34 Celsius degree plus 273. This converts Celsius to Kelvin. Similarly, we can do that for T2. Then we can substitute the numbers in this conversion, and we find out P2 is 1.25 times 10 raised to 3 millimeter mercury. I want to emphasize a couple of things for one more time. First, all the temperatures must be converted to Kelvin scale, as you see over here. However, for the P and the V, as you see, they can be units other than ATM, as long as P1 and P2, they share the same units. And the V1, it's milliliter. V2 also share the same units, so they can cancel out. To sum it up, P and V can use different units, but under two different conditions, those pressures, P1, P2, must have the same unit, and V1 and V2 must have the same unit as well. Let's move on and talk about another gas law. This is the Avogadro's gas law, which deals with the relationship between volume and moles. Avogadro's law states the volume of a gas and the amount of gas in the moles are directly proportional, assuming constant temperature and pressure. So V is directly proportional to N, or the number of moles of gas. You can also write it as V1 over N1 is V2 over N2. As you can see in the picture, as the number of moles increase, the volume also increases for all these data points. A 4.8 liter of sample of helium gas contains 0.22 mole of helium. How many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liter? So as you read this, you know you have V1 over here and you have N1, and how many additional, read this carefully, it's not the final total number of moles of gas, it's additional gas. Okay, so additional, but we can find that the additional means that it's a N2, it's the final minus N1, that's additional. So we need to find out N2 first. Okay. What about volume? Volume, it tells you it's V2, it's 6.4 liter. We use Avogadro's law for this calculation because it's the relationship between volume and the number of moles. So we use V1 over N1 is V2 over N2. So we find out N2 first mathematically and substitute the correct numbers in. Then we do not stop over here because this N2 tells us that's the total number of moles of gas we should have in the end. So the moles of gas to be added is the total minus what we originally have, which is 0.22 mole. So you should add 0.07 moles more gas into the sample in order for the sample volume to increase to 6.4 liter. A 36.1 milliliter of sample of oxygen gas contains 0.529 moles of oxygen. So you have volume here, V1, and then you have N1. If enough oxygen is added to the sample to obtain a volume, so that's your V2 of 50.5 milliliter. So what must be the final mass of the sample? How do you find the mass of the sample? Remember, mass can be found by this relationship. So mass is moles times molar mass. And the molar mass can be calculated based on the molecular weight of, or formula weight of particular formula. So let's work on this question. We need to find out the moles because the molar mass for helium can be looked up in the periodic table. Let's solve this problem step by step. So first, we know we have a V and the N relationship because we do need to find out the N2. Okay, so V1 over N1 is V2 over N2. So this gives us N2 equals V2 over V1 times N1. So we substitute the numbers in. This equals V2 is 50.5 milliliter. V1 is 36.1 milliliter. And times 1, 0.529 mole. this is 0.740 moles. To remember, the question is not asking you how many total moles of gas you have. It's asking you what's the final mass. So here's the moles. Then we can find out the mass. So mass will be moles 0.740 mole times the molar mass. So for helium, you look up the molar mass. Excuse me, this is not helium. This is oxygen. Yeah, because it's oxygen gas we are talking about. Okay, so oxygen gas, the molar mass is 32.00 grams per mole. So moles cancel out. This gives us 23.7 grams. So D is the correct answer. Let's summarize everything we have learned so far. We have learned Boyles Law, Charles's Law, combined gas law, and Avogadro's Law. Can we put them together? If we combine all these laws together, we actually have one law that is called ideal gas law. And when we rearrange this ideal gas law, it can be written as P times V is nRT. So PV is nRT, is the ideal gas law, which tells us the relationship between the four variables P, V, N, and T. The R is the ideal gas constant. When you look at the ideal gas law, you need to pay special attention to the units. Previously, when we talked about Boyles Law, Charles's Law, combined gas law, and the Avogadro's Law, we mentioned one important fact, which is temperature in those gas laws previously must have a temperature of Kelvin. However, all the other units, as long as condition 1 and condition 2 have the same units, then it's fine. In the ideal gas law, it does not talk about two conditions. Rather, it talks about one condition only. There's no change of the variables. We have 4 different variables in one condition, which is put in the ideal gas law. PV is nRT. In this case, the units must be correct. Pressure, in this case, it must be in atm. Volume must be converted to liter. And the amount of gas N must be in moles. Temperature, again, must be in Kelvin. And the R, ideal gas constant, is 0.0821 liter times atm per mole per K. With the ideal gas law, we can actually convert it to many other forms of different gas laws, including the ones we have talked about. For example, because P, V is nRT, so we rewrite the ideal gas law, okay, and convert it to PV is nRT, because if N and T is not changing, then the right side will be the constant. For this reason, P times V is a constant, or under both conditions, P times V are equal. Similarly, if we convert this ideal gas law, PV is nRT, to V over T equals nR over P. So if N and P are not changing, then the right side is a constant. And this gives us the Charles's Law, which is V and the T relationship. And you can look at other different laws as well as listed over here. For example, Avogadro's Law, which is V and N relationship. and the Gay-Lussac's law, which is the P and the T relationship. We can also derive the P and N relationship. For an ideal gas, which two variables are inversely proportional to each other, assuming all other conditions remain constant? So do remember, for ideal gas law, PV is nRT. According to Charles's law, which is under constant moles of gas and constant temperature, P and V is inversely proportional to each other. So A is the correct answer. Calculate the volume occupied by 0.845 mole of nitrogen gas at the pressure of 1.37 atm and the temperature of 315 Kelvin. When we look at this question, the first thing we should notice is that there is no change of states. It's only one state. There is no initial and final states. So we are going to use PV is nRT, or the ideal gas law, to solve this problem. Please note, in the ideal gas law, all the units must be correct. So PV is nRT. We need to find out the volume. So V is nRT over P. Over here, we have the units. Every unit is correct. If any unit is not the right unit, you have to convert it to the right unit. For example, the amount of gas N must be in moles, temperature must be in Kelvin, and the pressure must be in liter. So we substitute the numbers in. And here's the moles, and here's the R, and here's the temperature, and that's the pressure. So we find out the volume is 16.0 liter. Let's look at another example. Use the ideal gas law in combination of a mass measurements. A sample of gas has a mass, and its volume is given, and the temperature is also given. The pressure is given. We want to find the molar mass. Remember, what is molar mass? Molar mass is defined as one mole of mass, 1 mole of sample, and how many grams is inside. So basically, molar mass is the same as saying mass over moles. Remember, moles can be found using ideal gas law, because in ideal gas law, PV is nRT, so N is PV over RT. Please make sure when you solve this problem, use the correct unit. Again, in this example, all units are correct. If not, you must convert the pressure to atm and the volume to liter and temperature to Kelvin. In this case, all units are correct. So we substitute the numbers in and calculate this, and we find out the moles. After we have the moles, mass divided by moles, that's the very definition of molar mass. So we find out the molar mass is 28.0 grams per mole. How many moles of an ideal gas are in the container with the volume of 5.2 liter at 580 millimeter mercury and at 20 degrees C? So let's look at this example. Apparently, there's no initial and final conditions. There's only one state. So we are going to use ideal gas law. PV is nRT. We need to find out how many moles of gas you have. Okay. Do we have P? Yes, we do have P, but remember, this P must be converted to atm. And volume is given as well. Temperature must be converted to Kelvin. So this T is given. Given. The only thing is we need to convert them to correct the unit. So N is PV over RT. So P is 580 millimeter mercury. Remember, 1 millimeter mercury, 1 ATM is 760 millimeter mercury. So 580 divided by 760, that gives us ATM as the unit. V is in the correct unit, 5.5 liter, divided by 0.082, 1 ATM liter per mole per K, times temperature. Temperature will be 273 plus 20 degrees C. This will convert to Kelvin. So after we do the calculation, the answer is 0.174 moles. C is the correct answer. Let's look at another question. First, folks, please remember, when you read the ideal gas law questions, first you need to decide, are there two conditions? If two conditions, you're going to use Boyles Law, Charles' Law, combined gas law, or Avogadro's law. But if there is only one condition, use ideal gas law. Let's read the question. We have certain grams of a sample at a certain temperature. So we do have a T and a volume. We have a V and we have a P as well. Then we want you to identify the gas. How do you identify the gas? One of the important property of a gas is the molar mass. So we can identify the gas by looking at the molar mass. We have grams over here, grams over moles, that gives you molar mass. So we need to find out the N first. We have three conditions known, P, V, and the T. So N is not known. PV equals nRT. So N is PV over RT. Please remember, all units must be correct so you can get the correct answer. And P must be in ATM, and it's a 1.00 ATM. It's already correct unit. V is in liter already. R is 0.082, 1 ATM liter per mole per K. And the temperature over here is in Celsius degree. You must convert it to Kelvin scale. So that would be 38 plus 273 Kelvin. So let's find out what the answer is. The number of moles is 0.0587. We need to find out the molar mass so we can identify the gas. Molar mass is mass over moles. So mass is 4.17 grams divided by 0.0587 mole. This gives us 71.0 grams per mole. So we can calculate the molar mass for each gas over here. This molar mass is 2 grams per mole. And the second one is 28 grams per mole. Fluorine is about 38 grams per mole. Oxygen is 32 grams per mole. And chlorine is 71 grams per mole. So the identity for the gas is chlorine. Now let's talk about so-called molar volume. Molar volume is the volume occupied by 1 mole of gas at 0 degrees C and 1 ATM. And the volume happens to be 22.4 liter. And the conditions for 0 degrees C and 1 ATM, they are called the standard temperature and pressure. for ideal gases. Standard temperature is 0 degrees C or 273.15 Kelvin. The standard pressure is 1 atm. For gases, for reactions, slightly different. Okay, right. We can actually calculate this volume for all gases because PV is nRT. So V is nRT over P. So if it's 1 mole of gas, so 1 mole times 0.0821 atm liter per mole per K, and T is 273 or 273.15 Kelvin, divided by P is 1.00 atm. When you do this calculation, this gives you 22.4 liter. What this tells you is all ideal gases, no matter what the identity is, 1 mole of any ideal gas would occupy exactly the same volume, which is 22.4 liter, and 2 moles of any gas would be twice as much. It would be 2 times 22.4 liter, that is 44.8 liter for 2 moles of any gas. So for example, 1 mole of helium, it gives you 22.4. And 1 mole of xenon gives you 22.4 liter. But the mass is different. This just tells us the volume is the same, but mass is different. Then the density, which is mass over volume, will be different. How do we calculate the density under the standard temperature and standard pressure, or so-called STP? Since we know 1 mole of any gas will be 22.4 liter, and 1 mole of any gas will also contain molar mass grams, which means the mass is the molar mass for any mole. That's the very definition of molar mass, right? How many grams in 1 mole? Okay, so mass for 1 mole, that's molar mass, and the volume for 1 mole is molar volume. Molar mass divided by molar volume. That gives us density. Let's look at one example. Calculate the molar mass of a gas that has a density of 1.70 grams per liter at standard temperature and pressure. Under standard temperature and pressure, the molar mass over molar volume will give us density. Molar mass is unknown. Molar volume is 22.4. Density is known. So we can calculate molar mass, which is density times molar volume. Remember, molar volume, you don't have to recalculate. It is 22.4 under STP. So density is 1.70 grams per liter, and the molar volume is 22.4 liter per mole. So liter is cancelled out, and we calculate this. This gives us 38.1 grams per mole. E is the correct answer. As we previously pointed out, gases are not always acting ideally. Only under high temperature and low pressure, the gases will behave ideally. Under low temperature and high pressure, the gases will not behave ideally. The reason is because under low temperature and high pressure, the particle size is significant compared to the space in between the particles, and the interactions between the particles, they are no longer negligible. They are actually significant. For this reason, under low temperature and high pressure, the gases will behave less ideally. Let's look at this question. A real gas can approach ideal behavior under what condition? We have discussed this very thoroughly. It's under low pressure and high temperature when the real gas will behave more ideally. So D is the correct answer. Low pressure and high temperature, a real gas will behave more ideally. Let's look at Dalton's partial pressure law. This tells us how a mixture of gas samples will behave. According to kinetic molecular theory, because each component in the mixture, they do not attract or repel each other, so they act independently of the others. So for this reason, the pressure due to any individual component in the gas molecule is going to be contributing independent of others. So the total pressure will be the contribution for all samples like sample A, sample B, sample C, etc. P total is all the partial pressures of all components added together. And the contribution from each component is the fractional component of that component times the P total. The fractional component, or sometimes we call this mole fraction or volume fraction, because according to Avogadro's law, a mole fraction is going to be the same as volume fraction. So PA sometimes is written as, this looks like an X, but it's called a chi. This leg is a little bit longer. Chi A times P total. Chi is the mole fraction. Let's look at one example. A mixture of helium, neon, and argon has a total pressure of 558 milliliter mercury. The partial pressure of helium is given, and the partial pressure of neon is also given. So we ask, what is the partial pressure of the argon? Remember, the total pressure comes from the contribution from all components individually. So P total is all components added together. So for this reason, the argon contribution is total minus those contribution from helium and the neon. And we put the numbers in so we can find out contribution from argon, which is 105 millimeter mercury. The partial pressure in the mixture of three components, carbon dioxide, nitrogen, and oxygen, in a sample is given respectively, and calculate the molar percentage. So do remember the contribution from each component, for example PA, PP, or PC, it's the same as the mole fraction or mole percentage times the P for total. So the mole fraction will be P, the partial pressure for that. PA, that means the A means component A. A could be carbon dioxide, nitrogen, or oxygen in this case, right? Divided by total. So for this reason, the mole fraction for carbon dioxide will be PCO2, or the partial pressure for CO2 divided by P total. CO2 contribution is 50, so it's 50.0 atm divided by the total 50.0 plus 495 plus 205. This is 0.066 6.7, or that's the same as 6.67%. Okay. And we can do the other calculations similarly. For example, chi for nitrogen, it will be partial pressure of nitrogen divided by P total. Okay. And this gives us 0.660 or 66%. Next, we can also calculate the mole fraction for oxygen. That's P for oxygen, which is 205, okay, divided by P total. Total, you add all contributions together. This gives us 0.273, or the same as 27.3%. According to our calculation, B is the correct answer. Let's see how Dalton's partial pressure law can be used to our real-life experience like mountain climbing. To remember, under normal situation, the ambient pressure is going to be 1 atm, and we do know the percentage of oxygen is 21%. So for this reason, normally our lungs will breathe oxygen at a partial pressure of 0.21 atm. On the mountain, on the top of Mount Everest, the total pressure is not 1 atm. Rather, it's much smaller. It's 0.311 atm. So the partial pressure of oxygen will only be 0.065 atm. The low oxygen level will cause so-called hypoxia or oxygen starvation. The mild hypoxia will cause dizziness, headache, shortness of breath. Severe hypoxia, which occurs when the partial pressure of oxygen drops below 0.1 atm. This may cause unconsciousness or even death. So climbers hoping to make the summit of Mount Everest usually carries oxygen to breathe. So we just learned low oxygen level or hypoxia can cause negative psychological effects. So does high oxygen level. For example, when the scuba divers are 30 meters below water, they will undergo 4 atm of total pressure. So this will make the partial pressure of oxygen 4 times as much. So rather than having 0.21 atm, the partial pressure of oxygen will be 0.84 atm. And this results in higher concentration of oxygen in our body tissues. When the partial pressure of oxygen increases beyond 1.4 atm, the increased oxygen concentration in body tissues causes oxygen toxicity, characterized by muscle twitching, tunnel vision, and convulsions. Divers who venture too deep without proper precautions have drowned because of oxygen toxicity. Too much oxygen will cause negative physiological effects. Too much nitrogen will also have negative effects. When the partial pressure of nitrogen increases above 4 atm, nitrogen narcosis, also referred to as the rapture of the deep, will happen. And divers describe this condition as being tipsy, and judgment may become impaired. To avoid oxygen toxicity and nitrogen narcosis, deep sea divers breathe the specialized mixture of gases. For example, heliox is a mixture of helium and oxygen, usually at a smaller percentage of oxygen than would be found in the air, thereby lowering the risk of oxygen toxicity. Heliox contains helium instead of nitrogen, eliminating the risk of nitrogen narcosis. In the next few slides, we're going to talk about the gas pollution. And the air pollution comes from a number of sources, including electricity generation, motor vehicles, and industrial waste. Sulfur dioxide is emitted primarily in electricity generation and industrial metal refining. And sulfur dioxide is a lung and eye irritant that affects the respiratory system. Sulfur dioxide is also one of the main precursors of acid rain. Carbon monoxide is formed by incomplete combustion of fossil fuels. It is emitted mainly by motor vehicles. Carbon monoxide displaces oxygen in the blood and it causes the heart and lungs to work harder. At high levels, carbon monoxide can cause sensory impairment, decreased thinking ability, unconsciousness, or even death. Ozone in the upper atmosphere is a normal part of our environment. Upper atmospheric ozone filters out part of the harmful UV light contained in the sunlight. However, ground level ozone is an eye and lung irritant. Prolonged exposure to ozone has been shown to permanently damage the lungs. Nitrogen dioxide is emitted by motor vehicles and by electricity generation plants. It's an orange-brown gas that causes the dark haze often seen over polluted cities. Since the passage of the Clean Air Act in the 1970s, the pollutant levels in the U.S. cities have decreased significantly over the last 30 years, as you can see in this picture. So that's it for today. Have a good day. Bye-bye.